Hi all, we are going to start a new presentation of the third gvSIG festival. This presentation is about the Horton Machine, new geoprocesses for gvSIG desktop. The speaker is Silvia Franceschi from the hydrologist company, but she hasn't been able to be live. And I'm going to share my desktop to share a video with the presentation. Silvia is going to give the presentation. So I'm going to share desktop first. And now I'm going to start the video.
Good morning, everybody. Franceschi, and this presentation is about the Horton Machine library and the new geoprocessing project. So who am I? Definitely, I am an environmental engineer specialized in hydrology, hydraulics, geomorphology, and forestry. I have a PhD in marine environmental and agriculture, and together with Andrea Antonello, I'm the founder of Hydrology, which is a very small engineering company based on the northern Italy, and since 2-3 years we are member of the gvSIG association. My work is mainly dedicated to develop scientific models contained in the Horton Machine JPress2 library in the fields of hydrology, hydraulic, and forestry. I'm also an OSGeo charter member. What is so this I thought presentation is about the Horton Machine library, but what is this Horton Machine library? What does this contain? The Horton Machine library is an open source geospatial library focused on the hydrogeomorphological analysis and environmental modeling. The development of this started in 2002 at the University of Trento and continued with the Foundation of Hydrologists in 2005. And from 2015, it is integrated as a special toolbox inside gvSIG GIS. Now it is available for installation through the gvSIG Update Manager. If you install the Horton Machine package in gvSIG, you will see in a new item in your menu bar that is called Edge Machine. If you click on it, you can see there that there are different sub-items, sub-menus. The most important one is the special toolbox, containing definitely all the Horton Machine library. And then there are some other tools that we will see during this presentation, containing useful information, tools to analyze and prepare the data for the analysis with the Horton Machine models. Inside the spatial toolbox, you will see here there are different modules divided in sections and subsections. The main section is the Horton Machine, which is the section containing all the geomorphology tools for the analysis of digital terrain model. Then we have tools for raster and vector processing, and then mobile tools to support the interaction with the GeoPaparazzi application for digital field mapping. And the last one is developed is the Lesto tool, which is a tool containing two algorithm and items for LiDAR analysis, mainly dedicated to forestry analysis. If you select a module from the module list on the left of the graphical interface, you will see on the right of the graphical interface all the needed parameters of the model. One nice thing is that it is possible to select the map to use from the maps that are loaded in the active map view of gvSIG. Then you can define the module parameters. And then to run the model, you can decide to run the model as it is in the graphical interface, or if you want, you can save a script containing this model and these parameters, or load an existing script coming from another coming from the file you previously saved and edited or something like that. Take care to define these additional things in the graphical interface. For example, if you want to show also the experimental modules here in the bottom, you have to leave this click, otherwise you have to unclick these experimental modules, and you will see only very tested and approved modules of the Horton Machine library. Then there is this debug mode. It is useful to see all the messages coming from a tool, and I definitely recommend you to use this debug mode if you have some problem, and if you want to send us some if you want to ask us for information in the mailing list, please send us the log using this debug mode. And then here you have another very important thing. If you have big map, you need very high memory, lot of memory. So you can set here the maximum memory available from the one that you have on your computer. So let's see a bit the content of this Horton Machine library. For example, in the geomorphology section, you have tools for the base analysis of the digital terrain model, for example, the extraction of drainage direction, total contributing area, the extraction of network and watershed, evaluation of scale distances, slope, curvatures, and hydrological and geomorphological indexes and attributes. We have also a section dedicated to statistics, where you can find tools for doing a statistical analysis between different rasters, raster maps, and also for the interpolation of meteorological data with kriging, or in general with GEMI, which is a tool that interprets mainly dedicated to temperature, pressure, humidity, and wind, and all the meteorological information that really depend on the elevation. Then there is the section dedicated to hydrogeomorphology. This section contains definitely the main models we developed. For example, peak flow is a model to evaluate the maximum discharge related to a given precipitation, but it also works with statistical information of the rainfall duration intensity duration curves, as suggested by the European Flood Directive. As you can see here, peak flow produces the complete flow hydrograph for the different return times. Also related to hydraulic, there is also a simplified one-dimensional hydraulic model based on the Sandman equation, where input and output are based on GIS layer, and calculates the water depth and velocity in each section. The very nice thing of this tool is that it can handle lateral contribute, so both inflow and outtakes. In the field of hydraulic, there is also a tool to prepare the data for the A-class one-dimensional hydraulic software. Then we have here also the possibility to evaluate the hill slope stability, and in particular the hazard related to shallow landslides. And the tool, the model is called ShallStab, and it can be used to evaluate the stability condition for the given precipitation, but also to evaluate the critical rainfall in each pixel. Mainly dedicated to the evaluation of natural hazard in mountainous region, there are tools dedicated to the evaluation of debris flow. All these tools are based on geomorphology analysis, and there are tools to extract the triggering points, then also to propagate this the debris in the network, and the final propagation in the farm, on the farm. Also related to the flooding problem, natural hazard, there is the problem of the large goods transportation during flooding events. It is possible to evaluate the available vegetation in each section using the tools inside the Horton machine, and in particular by evaluating the vegetation on the unstable and connected areas. In this way, you can calculate the contribution, the local contribution of each hislop in each section of the river. As you can see here, there are sections that contribute a big contribute, the one with big dots here, the section that have only small contribute, and section without any contribute. This local contribute will be propagated in the network with a simplified 1D hydraulic model and some useful conditions to evaluate the possible clogging section. And the clogging section are highlighted as critical section, and you can do this analysis for each single stream inside your basin, and then put all the results together and highlight the critical and non-critical section for all your basins. The very important thing of these tools is that for each critical section, the tool saves the important parameters in the attribute table. So you have the volume clogging the section, the average height and average diameter of the clogged material, and also the origin of the material. Last but not least, we have the last implemented section, that is raster. It is the LiDAR and Power Science Toolbox open source. It is the section where we have the tools dedicated to LiDAR analysis, and in particular for forestry analysis. It has been developed in collaboration with the Free University of Bolzano, and contain tools, for example, to interpolate point cloud data, to extract digital terrain model and digital surface model with algorithms such as adaptive scenes or inverse distance weight from the raw point cloud. There are also tools for extracting the building from the LiDAR dataset, and finally tools for the analysis of vegetation, mainly dedicated to extract tree tops from raw point cloud, but they also work on raster data. With this tool, the aim is to extract the position and the main characteristics like height and diameter for each single tree inside the given area. So, since now I just show you a very panoramic view of some tools inside the Horton Machine library, but there are many other, and I will suggest you to try and have a look of the list of the modules available. Now we will see some other tools we developed and are available in gvSIG for helping you to manage the data, preparing the data for the analysis and analyze the results. The first one is the MapCalc tool. That is a tool that can be used to perform map algebra on raster maps. It is very easy. This is a typical formula if then else of our MapCalc. And for example, in this case, if you want to know which part of an elevation model is between which part of an elevation between 1,000 and 1,300 above the sea level looks towards south, so it is exposed to south for agricultural purposes or to localize some ecosystem environment or something like that, you can use a formula like this. First of all, you have to evaluate from the DTM to calculate the aspect map using the aspect tool inside the special toolbox. Then you can use a formula like this. If the digital terrain model is greater than 1,000 and less than 1,300, and the aspect, which is a map of degrees, is between 160 and 200, then the resulting map, put in the resulting map the elevation, the content of the digital terrain model. Else, do not put anything, put a no value. Here you will see the same formula inside the graphical interface. As you can see here, there are some very interesting hints in the graphical interface which help you to fill the formula in the right way using the right syntax. And here you can choose the maps available and loaded in the map view. On the right here of the screenshot, you can see the output map. The output map, in this case, contains only the sites of the area with an elevation, the elevation of the sites with an elevation ranging from 1,300 and exposed to south. In the Horton Machine menu package, we also have a full integration of EPINet software, which is the software developed, very powerful and well-known software developed by the Environmental Protection Agency of the USA for the evaluation for the design and management of water supply system and for water quality analysis. You don't need any installation of EPINet. All is inside the plugin, so you have all the tools to prepare the data, to run the simulation, and to evaluate the results of the simulation. Other interesting tools, as you can see here from the 8 machine menu, the last item here is called tools, and it contains some other useful tools like the position info, which is a tool that gives you the coordinates of the clicked point in a very special graphical interface. WKT geometry tool is gives you the information, the well-known test of the geometry you select. PRJ tool adds the projection file to your data, which can be also a raster or a vector data. Feature browser is a tool which browses each feature inside a vector layer, automatically zooms on this picture and show you all the attributes of each single feature. And the last one is the raster styler. This can be used to quickly define a color table for a raster layer. It is mainly dedicated to raster with data inside, such as those derived from the digital terrain model, and not really for images. The raster styler can be accessed from the main menu, as you saw here, we can see here, but also from the context menu of the right click on the highlighted raster layer in the map view. For example, with this tool, it is possible to define easily you can select here the color table from the drop-down menu and then apply it. For example, in this case, if you want to quickly style the map of aspect, which is a map containing degrees from 0 through to 360, ranging from north and going clockwise. It is usually to define this color table starting from white to black between 0 and 180, and from black to white between 180 and 360. So that needs 3 rules, very easy. You can define it and apply, and then you will see your nice aspect map. The raster styler also supports transparency. If you style, for example, the digital terrain model with the elevation color ramp with some transparency on the aspect map, you will see a nice result with a simil 2D and a half representation of your base, of your digital terrain model. And then these other two additional tools. The first one is the raster graphic view. This can be used to analyze the content of the map. It can be used to analyze a small portion of the map where the color table is not sufficiently defined to understand enough the different values. And in this case, the raster graphic view shows you directly the content. On the map view, the grid raster cell without any text, or the raster values inside the cells, the columns and rows, or also the steepest flow direction between the cells. As you can see here, just right click and select raster graphic view. You can select what you want to see from the raster graphic view, and then refresh. You will see all the information you need. So definitely row and columns, the content of each cell, only the grids, and also the steepest flow direction between cells. And the last one, also to analyze a very small portion of map, is the raster value copy. The raster value copy, once triggered, copies all the portion of map visible in your map view into the system clipboard, ready to be copied in a new text file as in the format of an ASCII raster map. Then you can save it directly on as area.ash, and you can load it as ASCII raster map again in gvSIG or in another in your favorite application. Be careful to export to zoom on a small portion of the map because it doesn't handle too many values to save. But it also handles the no value data. As you can see here, the white part here is no value, and here we have the no values inside the text file. So I think it is all for now. This was a short introduction of the content of the Horton Machine library. These are some useful links: the homepage of the project, the mailing list, and some two other links where you can find some updates and information where we post new information about the project. So thank you for your attention. So welcome back here. This is a short video about the integration of the Horton Machine library in gvSIG. I'm Silvia Franceschi, and in this video I will show you how to start with the hydrogen morphological analysis on a digital terrain model using the Horton Machine library tools, the tools inside the Horton Machine library integrated in the gvSIG GIS. So first of all, you have to create a new project in gvSIG. So just create a new project in gvSIG and create a new view. Okay, view here. So please take care to define the projection of the view as the projection of your digital terrain model. And please be careful that this projection has to be in meters and not in degrees. So basically, the projection of the digital terrain model has to be a metric projection and not to be a latitude longitude projection. So apply here, yes. So now we can import our digital terrain model. So just drag and drop from the Explore to the map view and select normal. Okay, this is the digital terrain model. Define the projection. Okay, and now it is loaded in your map view. So since it is loaded as a grayscale color, we can give it a very nice color table with just a simple and easy tool you can select the layer here, right click and select the single band raster layer here, styler, and select here elef as color table, apply it, yes, and it comes here the nice color table with the elevation. As you can see here, you can see also the elevation in the different colors. Okay, if you have some interesting data that can be useful for your analysis, you can also load them. For example, I have the full vector layer of the rivers. Okay. And also in this case, you can style it here using a blue color because they are rivers. Okay, perfect. So now we are ready to start with our hydrogen morphological analysis. So select from the main menu of gvSIG in the H machine item here, you have to select Spatial Toolbox, and it will open the Spatial Toolbox here. Okay. Here you have the list of modules. If you open Horton Machine, you have different sections: basin, dam manipulation, geomorphology, hill slope, hydrogeomorphology, network, and statistics. If you don't know where are your tools, just open each section and you will see all the tools. So first of all, starting with with the geomorphological analysis, you have to make this digital terrain model hydrologically compatible. So definitely to remove the pits in the pits present in this digital terrain model. In this case, we use the pit filler algorithm. So we have we can choose it. We can look for the pit filling by pressing here in the search square of the modules pit, and then it will become pit filler and the pitter, or just go in dam manipulation and select pit filler. Okay. Here on the right of the graphical interface, you can choose the map from the available maps that are loaded in the map view, for example, digital terrain model, and select where to save the output map. In this case, we will save it in a map that is called pit.ashi. Please take care of two things. Horton Machine needs that you specify the extension of the output file. In this case, we for rasters, we just handle TIFF and ASCII file. So you can select both one or the other, either one or either TIFF or ASCII file. And then also be careful to give significative names to these rasters, to the output map. So otherwise, you will have at a certain point a lot of maps with the same names, and you will understand anything about the content. So in this case, pit, that is the output of pit filler ASCII map. Okay, save it like this, and then be careful here to have enough memory to elaborate this, to do this elaboration, and select from this drop-down menu the available memory RAM of your PC. I already did. And then now we can run with this button here in the upper part. So start the current module, and then it will start, and it opens here a box dialog where you find all the information. For example, the number of pits to solve and the progress of the work. It was very easy and fast because it was already no pits. Okay, so now we have this map as our base map for hydrological analysis. Also in this case, we can access to the single band raster styler and select the elevation color ramp and apply it. Maybe we can also give some opacity of the 70% and apply it. Okay, just for fun. Okay, now we are ready for doing all the other hydrological analysis. For example, hydrogeomorphological analysis. For example, it is possible to one very useful and easy hydrogeomorphology analysis is the elaboration of the aspect map. This part of tools useful to do geomorphology analysis are in the geomorphology section. So open it here, and you can see that there is the aspect, curvatures, and then also other tools that we will see in a while. So we select aspect, and then select the map here that on which we want to do the map of exposition, pit filler, and then select the output map here, and we call it aspects.ash. Okay, and run it again. Gives us the information about the aspect, yes, and it loads here the map of aspect. Unfortunately, the color ramp in grayscale is not so well defined, so we access another time to the single band raster styler and select the aspect or color ramp already prepared from 0 to 360 and apply it. Okay, very nice. So if we put this aspect map under the pit like this, we have this nice visualization of our digital terrain model that it seems a 2D and a half visualization of the digital terrain model. Very nice. So now we can do some other geomorphological analysis. I don't know what you want to see, but I like to see the map of slopes. So we can choose the gradient, so to visualize the gradient of the map. And so gradient here, yes, and then select always the pit filling and the gradient mode. This is standard default value is also fine. And then to define the map of gradient here, also gradient dot ash. Okay, save it and run it. Okay. In this case, we have also a nice visualization of the gradient, but if we want some colors there, we can select the rainbow map. Yes. And to give some opacity here. Why it doesn't work? So extra rainbow. Okay, there are some problems. Okay, it was just a bit slow. So put this one and do it again. Put this rainbow. No, not radiation. Maybe. Okay, now I understand. Okay, this is the rainbow map and a bit of transparency. Okay, again, here you can see the results of the gradients. These are the steepest part, and in the valley we have the very plain part of the basin, right? It's very useful to understand how it is our basin here inside. Yes, and then you will see the values of the slope here. Okay. Okay. If you want, you can put the vector layer up, and so you will see all the information you will need. Okay. Perfect. So now we can go on with some other geomorphology analysis. for example, we can evaluate the flow directions from the bit filler, and the output here is flow.hash. Okay, run it. Okay, it has been shown all white, so we can select to style it as flow, and voila, here are the sub the different direction of the flows, which means yellow, the flow is going to east, and northeast, and so on. So you can also see them here. And again, if you give some transparency here, you can see the 3D visualization of this flow. Okay, nice. In the Horton Machine package, we have a nice tool to correct this flow, because flow is a simple 8-direction tool for the evaluation of the flow direction, the steepest flow direction between the cells. But it is possible to correct this flow direction considering the general gradient of the hill slope, and in particular we can use the drain deer algorithm. I definitely recommend you to use this drain deer after flow, because the flow direction are in output of this module are very are better than the ones in the flow direction, simplified flow direction 80. So you have here to select the pit elevation model, and the map of flow you already elaborated. If you want the map of flow direction only on network pixel, you can select here the network, and then all the other default values are fine for now. You will find some other information about these parameters in the Horton Machine manual. Then you have to define the drainage direction output, drain deer.hash. And this tool also performs the total contributing area directly, tca.hash, save, and then you can run it very fast. Okay, the map of flow direction, I usually delete this map of flow direction, because it gives us some confusion, and can create confusion when you have to select the map of flow direction. We want to use always the map of drainage directions. So this I will delete. Yes. So we will use the corrected flow direction, and also we want to style this corrected flow direction as drain flow. Yes. Okay. Perfect. And also the total contributing areas. Here are total contributing areas is only in the river stream, but we can also define the raster, the color table also for this, since it is the content of the TCA map in the Horton Machine is the number of the cells draining in that cell. So basically there are many cells with very small values, and then the stream network is the cell with the highest values of the total contributing area. So we use a logarithmic scale and apply it. So you will find some information. Then you can also modify these parameters, but not in this case, I think. Okay. So starting from this information, you can also go on and calculate, for example, I don't know, the curvatures or the slope, which is which means the slope between each cell following the flow direction, and so on other tools. But we want to go on to extract the river, the network from this digital terrain model. So we go to the network section and select extract network. And it asks us to provide the map of total contributing area, TCA. And then there are different modes to run this extract network. For example, it is possible to run only on total contributing areas, defining a threshold on the total contributing areas. And then, or either you can run it considering the flow direction if you want to use the slope in topographical classes. So there are other, or the map of the slope, and the map of aggregated classes if you want to extract the river only in concave sites, which has a slope between and you have to specify in any case the threshold on the map. In this case, we use only the total contributing area, so we have to specify the number of cells, the minimum number of cells to define it as a starting point of a river network. I don't know exactly here, but we can then do some kind of, usually we do some kind of calibration of this parameter, considering the available maps of the rivers, or considering the data you collected going on the fields. So you have to calibrate this parameter, considering also the resolution of the digital terrain model of the pit filling. In this case, we have a digital terrain model of 10 meters, so the threshold here on raster map can be, I don't know, 100, and yeah, we say that we work only with the total contributing areas, and here we select the name, network 500, so we also know that 100, sorry, the threshold we used for extracting this network. Save and run it. Okay, this is the extracted network. So we can just put the official map of the network on it, and if you like, you can style it as here you have network net. Okay, in this case it was not a really good idea, because in any case all is blue, but we can see from here and from other that okay, it is a bit too many details, so we can change this parameter to 300, for example, or 500, maybe better 500. Okay, and change also the name of the output file and run it again. Okay, and so let's put it here. Maybe 500 is too much, but okay, in this case for us it can be also good, but it is possible to put here, change it in 300, and again 300 here in the output file, and run it. Okay, so I think this is almost something that can be used. Okay, so I usually also here delete the two networks that we don't want to use, so delete them, yes, and style this network 300 as network. Apply. Okay. So we really don't need any time new the shapefile of the network. Okay. So now it is possible to do other analysis on the network, and it is also nice to have this visualization of the network and our basin. Some very interesting things can be extracted here, and you can do some analysis on the Hislop to channel distance, the evaluation of, for example, geomorphology or the manipulation. You can extract the distance from the network, the other information from geomorphology and other things. But what we want to do is now to extract a basin. So to extract a basin, we have to just select an outlet. If you have the shapefile with the outlet, so it's nice to load it and select that outlet. Otherwise, you have to zoom on the river network. Okay. Be careful to zoom on the river network because you need to click definitely on the network and not in the other places. Okay. I will show you here, and then select from the dam manipulation extract basin tool. Okay, in this case you can put here the northern and eastern coordinate of your outlet. If you know it, you can write here the coordinates. Otherwise, you just have to go, you have just to click on the map on the network, and then you see here that you have this the two field here are will be filled with the exact coordinate of the network. It is interesting because gvSIG uses the tool that you have loaded. So mainly the zoom is not so nice to have. If you use the panning and click on the network, it will give you the exact coordinate. Then you have to provide the map of flow direction, and then here we use reindeer. And then if you want to snap on the network and so on, if you want to fill all the other parameters. But finally, here there is the possibility to define the name of the raster map of the basin mask, and it is called basin.ashin. Take care to add always the extension, and then it is possible to create optionally the point vector of the outlet, and we create it outlet.shape, and also the polygon vector of the basin.shape. Okay, and then we can run it. If you select a very small portion of the basin, if you select a point that is not in the on the network, it probably will extract very small pieces of the basin. But in any case, you can select it again from here and try to go near the network. But if you use this tool with the pan and if you zoom, there are no problem. You will for sure find the right point where to extract the basin. Okay, in this case, I don't know what I did, but it loaded automatically only the raster basin mask, as you can see here. Okay, this is the mask of the basin. You can style it. I don't know if there is something to style this, but it is only definitely only a map with one inside the basin and null outside. So it is possible to use the rainbow map and see all the interesting information. Okay, like this. And then if, like in this case, for some reason the maps are not automatically loaded, you have just to go to your folder and select to show this basin.shape, load it, and voila. So we can visualize only it and give a transparency inside and a nice red border. Okay, yes. So we are now ready to do some other interesting analysis on our basin. Unfortunately, we do not have many time. I just will show you the next operation that you should do before going on with other analysis. And it is to cut out all the data inside this basin. So definitely it is we have a very simple tool. It is called cutout. It allows you to cut the basin, the map you select here on a mask. In this case, we want to, for example, extract the pit pillar only on the mask of the basin. Okay, if you want, you can specify thresholds, and if you want, you can extract the outside part and not the inside. And then put here the process map, and it is called my basin dot pit or basin dot pit. No, basin underscore pit dot ashim, or basin pit without the underscore, not dot. Save it and run it. All the maps you will use for your elaboration has to be cut on the region. Okay, in this case, it says that it doesn't recognize the input of the data. Okay, let's try again, but I think I also did it. Basin pit.ash. Okay, I just select this, and okay, so this is the problem. So it shows here the first map, the map of basin like raster map, but it takes then the first map here. So just either put this down, okay, and use this, okay, and then maybe it is better to use another. Okay, let's try again. Basin here, because it gave an error because it automatically takes the first one with the same name, and in this case I gave the same name to the shapefile and to the raster, so at a certain point he selected the shapefile and not the raster. Sorry, my fault. And no, so here is pit, here is the basin, and then here select basin pit fashion. Save. Okay, again, this problem, but so in this case, so I will delete it. Yes. And we'll see if it works now. Okay. Sorry for this misunderstanding, and my fault was to name it at the same with the same name, raster and vector. Style it as LF. Okay. As you can see here, this is the map of bit filler cut on the mask of the basin. You have to do it also for the map of the drainage direction, for example, and here you can define the basin underscore drain dot fashion, and then you can go on with all the maps you want only on the region of your basin, and which are also the maps that you can use to go on with some hydrogeomorphological tools. For example, if you want to use the rescale distance or the distance to outlet tool, it needs to understand where it is the outlet. So it asks here the map of flow directions, and so you have to select the basin pit, the map of pit filler, the map of flow direction, and basin drain. Here take care to select the basin drain and not the drain of all. And here is the basin distance to outlet. The output map. Okay, so if you style it with a nice rainbow map, you will see the distance to outlet. And at the same time, you can evaluate the rescale distance, which is the distance to outlet considering different celerity between the path on the wind in the hillslopes and the path in the river network. For example, the flow direction, here the basin drain, the network. We didn't, so in this case we need also the network map, so we have to cut out also this the network map before going on with this elaboration. So I think you can do it by yourself and going on to do some nice elaboration with the Horton Machine package inside gvSIG. If you have any question, please join the mailing list and ask us for help. We will be very happy to help you to improve these tools and spread this tool all over the world. Thank you very much. So good morning, everybody. I'm Cindy.
If you are interested in this plugin, you can ask at both Spanish and English mailing lists, and the presentation, the PDF file of the presentation and the video will be available at the third gvSIG Festival website. The video will be in YouTube too, in the gvSIG YouTube channel, and you can change the resolution to 720 if you have problems with the visualization. Okay, we are going to finish the webinar here, and we invite you to follow the next webinar of the third gvSIG Festival. See you. Bye bye.